Great. Well, it falls to me to occupy the hunger shift, the pre-lunchtime shift, and I don't know about you, but my stomach's rumbling, so I'll try and be as quick as I can. I'm going to take a slightly different tack to what has been done so far, and actually focus a little bit on where biodiversity and climate change policy is going, and what I perceive to be the fit between the tools that we're developing, both at the genetic level and at other levels, and also the requirements that we're going to have to fulfill things that our governments have signed up to over the next, few years, actually, a surprisingly short period of time. I'm going to talk a little bit about IPBES and also the Intergovernmental Platform on Biodiversity and Ecosystem Services, and a little bit about the Convention on Biological Diversity as well, because as a geneticist working at the interface with conservation and policy, these things are starting to impose and will impose on many of us, particularly if we're going for national funding, constraints on the kind of questions that we can pose in a sort of a more applied context. I'll talk a little bit about the question of resilience, resistance, and genetic diversity and the evidence out there, because one of the things that I'm constantly asked by policymakers who I run into is, does genetic diversity matter at all? Is there anything that we should be conserving? And that has been a huge issue for biodiversity conservation and genetics over the last couple of decades. Then I'll speculate a little bit about what tools we might need to chart population changes and responses within the context of the time frame that we have available. And then finally, I will look at a couple of case studies where we've been looking at changes in effective population size, firstly with the Bornean orangutan and then the equally glamorous Welsh polecat. So, I don't know which way to look here. So IPBES is currently, I don't know whether many of you have been involved in it, is currently developing its draft work program for 2018, and it clearly depends on lots of information on the role between biodiversity, its stability and resilience, and the delivery of ecosystem services, which, whether we like it or not, and I'm sure many of us don't, actually forms the basis for the rationale for protecting biodiversity into the future. We are no longer, certainly at the moment, in a situation where biodiversity can be conserved just for its own sake. The global rationale for conserving biodiversity is because of its provisioning of ecosystem services for our exploitation. Oh, for some reason. That's not working for some reason. Now it is. Thank you. Under the usually politically ludicrously short timescale that we're working to, one of the objectives under the IPBES strategy is to strengthen a knowledge policy interface on global dimensions of changes in biodiversity and ecosystem services. We need to scope this by December 2015 and deliver it by December 2018 on the drivers, pressures, states and trends of biodiversity and potentially on their impacts on human well-being. Particularly focusing on the Aichi targets. And for those of you who don't know what the Aichi targets are, they were the new set of targets that were developed under the Convention on Biological Diversity to halt the loss of biodiversity, originally by 2010, which was originally the Global Year of Biodiversity. As many of you will know, it was generally agreed that we had failed miserably to halt the loss of certain elements of biodiversity by 2010. So what did we do, or what did our politicians do? They set another target, and instead of having the Year of Biodiversity of 2010, we now have the Decade of Biodiversity, 2010 to 2020, and we have a new set of unrealistic targets to achieve by 2020. One of them is quite interesting from me as a geneticist, and that is that one of the targets that is there, the genetic diversity of a whole variety of organisms, but not just cultivated, farmed, and domesticated species, but also wild relatives of those species, socioeconomically important species, and here, interestingly, culturally valuable species, has to be maintained and strategies developed and implemented for minimizing genetic erosion and safeguarding genetic diversity for these species. And that sets us a big target, not at least because it's the first time that genetics has been explicitly referred to under the CBD since its inception in 92. So that means that one of the things that we're going to be doing is trying at a national level to understand the state of our genetic resources, both domesticated and wild genetic resources, in a time scale for 2020 so that we can report on what we've managed to achieve or what the state of biodiversity is at the genetic level. Quite a nice paper by Georgina Mason colleagues appeared in Tree a few years ago on the idea of ecosystem services and the processes that underlie ecosystem services and how they feed through ultimately to goods, which are, can be any kind of goods, both sort of everything from direct, very important goods such as drinking water through to culturally valuable services such as wild bird species, and ultimately to their value to people. Obviously, what we're, as scientists, mostly interested in are the fundamental ecosystem processes that drive the production of these goods. And under those circumstances, that is why the Objective 4 under the IPBES is urging us to get a better handle on what's going on. So for the next part of the talk, I thought I would come back to that within that policy context and ask a few questions about what do we know already about genetic diversity and the resistance and resilience of populations of wild species to anthropogenic change. Now, of course, intuitively, we all are, I'm sure, of the opinion that genetic diversity must be relevant to the viability of populations. But actually, if you look in the literature, partly because a lot of the work is experimental, and partly because a lot of the experiments that need to be done have to be carried out over quite a long time scale, there's rather little there that actually tells us something that we can easily package in terms of understanding those things, particularly for policymakers. There was a nice paper by Carlos Groh and colleagues a few years ago which talks about building evolutionary resilience for conserving biodiversity under climate change. I thought I would bring it back to climate change given the focus of this meeting, and a whole variety of different aims by which looking at genetic diversity, increasing and maintaining genetic diversity will allow populations to have a greater chance of survival. I won't read them out, but this is actually rather a useful slide particularly for interface with policymakers. I think the biggest driver for recognizing genetic diversity as potentially being important for the future is actually climate change. So the major components of this are really going to feed into climate change adaptation. Of course, there are some classic papers, and I'm sure many of you know these, where there is good evidence for the relationship between genetic diversity and ecosystem recovery. A couple of them are particularly focused on seagrass populations, but are nonetheless very compelling pieces of work which look at both climate change and actual direct anthropogenic disturbance and the relationship between genotype and other forms of genetic diversity in enhancing responses of populations to disturbance in the recovery phase. And recently there have been a few other papers, I just show a few here, which look at population performance, again, recovering in other species, for instance, in invertebrates. So there is a narrative that we can weave around the importance of genetic diversity in enhancing population recovery in the light of anthropogenic disturbance. And there's also related evidence. Here's some work by Di Battista back in 2008 who looked at a whole variety of data sets on genetic diversity and linked observed genetic diversity in a variety of different measures. Here I mean heterozygosity in populations that are undisturbed versus those populations that are disturbed. In this case, disturbed in many different ways, but even when you separate it out into different types of disturbance, the relationship seems to hold, except for the most fragile of organisms here in many cases. And so, for instance, in birds here, you see even greater genetic diversity in disturbed populations than in undisturbed. Perhaps one of the biggest problems that we have at the moment is one of the proxies that are usually used by global biodiversity scientists for ecosystem health is species richness, species diversity, endemism patterns. And people have looked, a number of people have looked over the last decade for a relationship between within species genetic diversity and species richness across different ecosystems, and some have found some quite striking results. A very interesting paper recently from Matt Strubig and colleagues on bats in Southeast Asia showed parallel declines in species and genetic diversity in tropical forest fragments, but there are lots of counter-examples as well. And another very recent paper by Pierre Tabelet's group showed a lack of correlation between within species genetic diversity in alpine plant communities. And so the jury is really out, and we need a lot more studies on that to be able to say whether or not there is such a relationship. But clearly, if there was, then that would simplify a lot of the work that needs to be done in preparation for 2020. So what kind of tools might we need to document this kind of population responses under very, very short timescales? There are a whole variety of different questions, and we've heard a lot about them already over the last couple of days, and I'm only going to focus on one. But clearly, phylogenetic diversity, other measures of genetic variation below the species level and population structure are very important. We've heard a lot about adaptive differentiation and the problems and prospects for detecting that at the molecular level at large scale. Population size change, including demographic change over short timescales, is something that we've focused on in some of the populations that we've looked at. And I'm going to focus on just a couple of examples, one on habitat size change, which is population fragmentation, and another one on ongoing introgressive hybridization. There have been, just to go back, in terms of measuring population size change and population status, genetic status, there have been obviously lots of developments in terms of measuring effective population size over the last couple of decades. One of the things I think that's quite important to mention is that clearly that there are a number of approaches that use both one sample estimates and multiple sample estimates. There's a nice paper by Barker a couple of years ago that compared many of these estimates in population of Drosophila and both linkage disequilibrium related estimates, single sample approximate Bayesian computation, SIB-SHIP assignment, the Podobkin heterozygous excess methods, and also Bayesian, full Bayesian coalescent simulations. And I think the important thing that came out of this was that although we do not expect these estimates to be similar necessarily, because they're often measuring different kinds of effective population size over different timescales, I think we're still quite clear that the two sample methods, or two or more sample methods, had lower coefficients of variation, especially when population size was small. The problem with that is that if we are going to be measuring effective population size and population size change between now and 2020, for most species we will only have a single sample to work with, because most species simply haven't been surveyed yet. And so, or we may only be in possession of a single data set. So one sample methods are probably going to be what we will have to be mainly working with in many of the populations that we're going to need to report on. So I'm going to talk a little bit about a couple of one-sample approaches that we have worked on, and with all of the caveats of which, Craig Moritz talked about this morning, in the sense that if you do have access to historical samples, it really does help in tightening your understanding of what's actually going on in terms of population change. Orangutans, this is a fairly old study, but we've updated it recently. We studied orangutans in Borneo over the last 15 years now. And we know quite a bit about orangutan population decline because orangutans are fairly high profile, and we know a little bit about their numbers and distribution because we can survey them relatively easily in the wild. We know that the population in 1908, we estimate from habitat and carrying capacity that the population size at the turn of the 20th century was about 300,000. The estimate of 25,000 in 1980 already tells you that the population had pretty much collapsed at that stage. In 2008, the estimate for orangutans in Sabah was down to just 11,000. So it's a really very perilous situation and a population that's clearly on the slide. In Sumatra, the situation is even worse, and it's entirely likely that the population will go extinct within the next 20 years. And the major reason, of course, is habitat loss and habitat fragmentation. In eastern Sabah, where I work, that is predominantly due to the initial deforestation that happened, followed by the rampant plantation of palm oil monoculture, resulting in small tracts of forest in many areas being geographically isolated with almost no option for dispersal except by human-mediated translocation. To put this into some kind of a map, in the area that we work in, the Lower Kinabatangan, this is the Lower Kinabatangan Wildlife Sanctuary. There's a river that runs through it, a large river which orangutans cannot cross. And then there are a number of forest fragments which contain reasonably well-characterized numbers of orangutans that we have been studying. But the important point to mention is all of the white area around here is palm oil monoculture. So these really are very small islands of habitat that remain. So we, a while back, studied the genetic diversity in these populations, and using one-sampled full Bayesian methods, came to the conclusion that the population had collapsed effectively, both north and south of the river. We saw a dramatic change in effective population size compared to what the ancestral effective size estimate was. And this collapse was something that we thought would potentially elicit an immediate response in terms of the management of the population, which has in fact happened. Interestingly, we were able to date the decline predominantly or very closely to the beginning of forest extraction, which actually started wholesale with the arrival of the British East India Company at the late part of the 19th century. And that was only really 8 to 10 generations ago. Orangutans are very long-lived. But there was still some possibility that it could have been precipitated earlier at the beginning of cultivation, but certainly very unlikely to have occurred at the beginning of hunter-gathering 40,000 years ago. But there is a problem with this, and that is that in populations like these, this signature of population decline can be very easily mimicked by population structure in the coalescent sample. And a number of papers showed this using island and stepping stone models and looking at simulating the coalescent events within those populations and showing quite convincingly that could be giving rise to an equally profound signal. And in fact, particularly, Lunes Chiki and colleagues showed very, very nicely that there is a strong relationship between FST among populations in either an island or a stepping stone model, and the mean and variance in log of N0 and N1, the past and present population size, and that with FST values above 0.5, you fall into a region where we call of the detection of a false bottleneck using this method can be a real problem. When we looked at our data, and these are, we looked at did the simulations on both sides of the river separately, we found that certainly within one of the riversides we were falling into the area where we could be generating a false bottleneck because of variance in FST. So the only solution that we had to this problem was to go back and try and do this at a wider spatial scale and see if we could replicate the signature that we found here in the Lower Kinabatangan in other populations where sufficient orangutans still exist that we could try and look at whether or not the pattern was the same. And that's exactly what we did very recently. And one of the things that we did was we compared the signature of demographic decline that we found both in single populations and in multiple populations. For example, here with this population in Sabangao, and then comparing it with the combined population in the whole of central Kalimantan. And if we saw a difference in the signature of population decline, then we could reasonably assume that it was, especially because there are rivers between them, that we could reasonably assume that this was actually a result of population structure. In fact, we saw no difference really between the pooled samples from central Kalimantan and the Sabangao, both in the N0, N1 ratio and in the change in population size predicted. So in this case, the effect of pooling across demes did not affect the signature of population decline. In fact, what we've done is calculated and looked at these N0, N1 values for all of the populations that we've studied, and they provide a remarkably consistent story in terms of the strength of the population decline. Where they vary somewhat is in terms of what is the most likely cause, whether it be forest extraction, which is very, very recent over the last few hundred years, which seems to be the case for Lower Kinabatangan, as we originally showed, but also for Tuanan in the south, as opposed to favouring the onset of cultivation, which could be anything up to a couple of thousand years ago, which we see as being the preferred model for the other sides, Danang Valley, Sungai Lading and Sabangao. So the lesson for us is that there may be coincident signatures, but they may have different timings. So the timing and magnitude varies, and the onset of cultivation rather than recent forest extraction seems to be the preferred model for three other populations. Although hunter-gatherers arrived probably around 40,000 years ago on Borneo, there's still a possibility of signal from local hunting in the south of Borneo, but not from the north, because locals have never hunted orangutans as far as we are aware in those places. Also, multiple population bottlenecks could have happened, but we weren't attempting to detect that. So very quickly, another example, we have been studying this species, the polecat, which is a species under great decline across Europe. And one of the reasons for its decline, aside from persecution, is hybridization with its domestic descendant, the ferret. The ferret was domesticated somewhere in southern Europe, and we don't know how long ago that happened, and has escaped into the wild in many parts of the range of the polecat. And hybridization, certainly in the UK, is a major issue. The problem is that if all ferrets look like this, we could easily find them and eradicate them, but they don't. Many of them can look like this, which is almost indistinguishable phenotypically from a true polecat. So we've been looking at the genetic structure and differentiation between putative polecats and ferrets in the UK. And we've done so within the context of some fairly good evidence that the population declined from very high numbers at the beginning of the 19th century down to a very, very low number indeed just at the onset of the First World War, and has expanded subsequently from a very small part of West Wales. We know many of the reasons for expansion: relaxation from persecution, banning of the gin trap, increase in rabbit numbers, but one of the possibilities that, of course, could be driving this expansion is hybridization with ferrets. And so we looked at the distribution of genetic diversity using microsatellite markers in both non-hybrid assigned individuals and hybrid assigned individuals in different parts of the range. And we see this core area of relatively unhybridized polecats in Wales, but there are some hybrids, certainly on the lowland coastlands. But what this enabled us to do was go back and test the question whether or not we were accurate in understanding how low the population went and when it became very, very endangered. And so we took this area of the genetic distribution of these wild animals, and we also examined their demographic history. And we see again evidence for a really substantial demographic decline, a very recent one indeed as well. And the timing for us was very sensible, because it was somewhere between 85 and 130 years ago, which lines up very well with what we know about its lowest point. The effective population size estimate for at its lowest point, however, seems implausibly low, even if we expect something like a 10-to-1 NC to NE ratio. And this could be still the signature of small amounts of admixture in the data that we could not detect, because we were using just a few microsatellite markers, well, a dozen microsatellite markers. And perhaps what we now need to do, and what we are doing, is repeat this using much more high precision SNP-based markers, and many of them. Just to finish, biodiversity and ecosystem service sustainability under the IPBES has driven a recent initiative in the UK to actually examine this question in detail across British ecosystems. And one of the studies that's involved in that is one on upland river ecosystems in Wales that we're responsible in. And what we're trying to do, and getting back to Craig Moritz's response to a question this morning, is do a replicated design across catchments and among many different species. So we're looking at the genetic signatures of demographic decline or demographic resilience in 6 different species, 4 aquatic and 2 terrestrial, across this scale. And again, trying to do it in a replicated manner, such that we can, any effects that we detect, we can examine whether or not we see them in different sites, and if we don't see them in different sites, try to understand why. And we're looking at subannual to decadal level events, which, given the generation times for most of the species we're looking at, should allow us to detect concurrent patterns of demographic contraction and expansion. So hopefully that will allow us to actually try to get at some of the questions that we've been looking at more anecdotally in these other larger furrier species in the future. So I hope that sort of given you some idea of the policy interface. We're continuing to try and persuade the policymakers that genetic diversity is an important component of biodiversity that we need to conserve, but we don't have a great deal of time to do it. So if any of you are interested in the sort of ongoing policy initiatives to combine data sets that have already been produced for wild species, you'd be very welcome to come and have a chat with me. And thank you for your attention.